Good morning. Welcome to Krishna's classroom. Recall that we last time we proved two characterization theorems of connectedness. And therefore we have altogether now three different definitions of connectedness. Now what we prove is a result which we have already explored using the first definition. We try to prove the same theorem using the two other characterizations. So the theorem is this: what happens to a connected set mapped under a continuous map? We know that it's connected. That's what we see. So we once again the same theorem. Let matrix spaces. Let G from X to Y be a continuous map if X is connected, then Gx is so we are assuming G is a continuous map and X is a connected space. Then what we prove is that Gx is connected in Y, which means connected sets are mapped by continuous maps to connected sets. Now this theorem we have already proved using a different, the earlier definition of connectedness. Now let us prove this. We give two different proofs for this theorem. The first one, each using a different characterization of connectedness. They are very simple. The first one, here we use the existence of a continuous map from the space to the 2-point set, namely plus or minus. Okay. So we have X is connected and we have Gx contained in. Now we are exploring whether Gx is continuous. So the question is Gx connected? Let F be a map from what we are having is x here, a part of this is G. Now take a function from here to the point set. 2-point set consists of +1 and -1. So F is a map from here to these sets, that is the +1 and -1. Okay. Which is continuous. So if it is connected, then you are going to have the function to be or the function to be a constant function. That's what we have. So you have now look at F composition, G composition F. So consider this is of course your G and this is your F. So you take F composition. Now F composition G is a map from X to plus of X. And both F and G are continuous. Implies F composition G is continuous. So we have now set up a continuous map from X to 0, 1. Okay. Now we have some information about this. We know that X is connected, and we are looking at the status of Gx. Now you observe that since X is connected and F composition G is continuous map from X to ±1, we have and maps x to 1, we have F composition G F composition G is a constant map, and that is possible only if F is a therefore what you have is, so F is a map from Gx to plus or minus 1, which is continuous, and F is a constant map that implies Gx is connected. So that is one proof. I mean, it's a very simple proof. We give an alternative proof. The second proof is, assume Gx is not connected. If some space is not connected, then what happens is that we have shown that there exists a non-empty subset A, which is a proper subset of Gx, okay, such that it is both open and closed. If it is not connected, the residual. Therefore, there exists a non-empty proper subset of Gx, which is both open and closed. See, we have proved that if you have such a non-empty proper subset which is both open and closed, usually x and phi are having the property that both they are both open and closed. Now what we are saying, a non-trivial subset is also having this property. That is possible only when the space is not connected and vice versa. So if it is not connected, then this is going to be the case, and if in a metric space this is the case, then you can infer that that particular metric space is not connected. Okay. So we have a Gx. See, there exists Gx is not connected, then we are going to have this situation, namely that there is some proper subset of Gx which is both open and closed. Now, since G is continuous, okay, so we say let us give a name to this set. So let such that P is a non-empty and V is a proper subset of Gx. And at the same time, it is both open and and such a set exists because we are assuming Gx is not connected. Now, since G is continuous, now we consider G inverse of V which is contained in it, and G inverse of Gx slash, that is the complement of V in Gx. Now you see B is open, therefore, and G is continuous means G inverse of V is open. Now G is continuous. Open. Now both, of course, G inverse of V and are not, and they are also proper. Further, is empty. This is empty. And why? Because Gx slash P is open. Okay. Right? Why it is open? Gx slash V is closed. actually, because V is open. But V is also closed. Therefore, Gx slash V is open. Okay? Therefore, you see that G inverse of Gx is open. Therefore, it follows that G inverse of V is both open and closed. Which implies X is not connected. Okay, so we have proved that if Gx is not connected, Gx implies then this is if and only if from which it follows that X connected implies by a contrapositive inference. So that completes the proof of the theorem. So we have given two different proofs, each one using one of the definitions. And earlier we have proved it in the general scenario. Now what next? So we will try to look at some applications of these results. Okay. Especially this, the one that involves continuous map from the space to the set plus and minus 1. So, the circle S1 defined by is connected. So if you can show that S1 is a continuous image of some connected set, then it is done. So that is the strategy. So consider F defined from zero one defined by or you can write 0 to defined by one can easily see that this function is a continuous function. Continuous, f is continuous, and therefore, and f max up to, therefore S1 is now is an interval of R and therefore it is connected. So S1 is realized as a continuous image of a connected set. As a continuous image of connected set. Hence, it is correct. So that proves the result. Second example, you consider the set S xy such that xy x comma y xy is not equal to 0. See, in this case it is of course this from 0 to 2 pi you are mapping this. In this case, so the question is, what is the status of that is what we. So if you look at the given set is this. See, xy equal to 0, it's the complement of this. Xy equal to 0. Xy equal to 0 means either x equal to 0 or y equal to 0. So in R2, this is xy equal to 0. The pair of straight lines x equal to 0 and y equal to 0. That is the coordinate axis. So it's a complement of that. So we are talking about this. This is the set that we are discussing. Now, okay. Now, obviously, I mean, it is not connected at all. Okay, because it has been bifurcated, split up. So, let us try to prove this. So, define plus or minus 1 by f of x divided by. Now you see that this is a continuous map. Of course, since x is not, this is well defined. X is not equal to 0 on S, and it is continuous. Then you can see that F is a map from S plus or minus. Because when x is positive, takes plus 1. When x is negative, it takes a value. Okay. So you have a continuous map from the set S to plus or minus 1. Therefore, S is not, I mean, as we have observed that it is not coming from the nature of the space. So we give another example. 3 R2 and this is a hyperbola. So how does it look like? This is the point Yeah. So it looks, so it passes through the point 1 0. So this is this, right? Okay. There is no intersection with x equal. So these two are two branches of the hyper. You see, that's not connected. I mean, from the figure, it is clear that it's not connected. Now, once again, you can define equal to x divided by. Now you see that since x is not equal to 0, it's clear that it takes values plus 1 and minus 1. So you have, whenever x is positive, it takes a value plus 1, and whenever it takes x is negative, it takes the value minus 1. And you can see that this branch gets mapped to plus 1 and this branch gets mapped to minus 1. Because you see that x coordinate here is positive, the x coordinate here is negative. That's it. So by the definition, and f is continuous. Therefore, what we get is this. Therefore, you have f is on to and that's the next example. Shall take up the example. To complete. Once again, to define now you see more y is not equal to 0. Y is not equal to 0 in irrational. Therefore, f is continuous. and f is on. It's not a constant function. S is not connected. So we'll take up another example. Fine. Take up GL2R. What is GL2R? GL2R is all 2 by 2 matrices such that determinant of A is not equal to 0. Now what we claim is that GL2R is not correct. No. See, these are, at least you have a geometric guidance here. Now we are going to slowly look at more complicated scenarios. Now we claim that GL so let us define a map F from F of A equal to determinant of A modulus of determinant. Now you see that determinant of A is not equal to 0. Therefore, F is a map from continuous. So that needs slight small work to prove that it's continuous. And therefore, that is, there exists a continuous map this one, not constant. Which implies is not connected. It's not connected. We take another example related to it. Take O n now, which is defined as A belonging to such that A into A transpose equal to I. Okay. Now you observe that which is equal to 1. Now determinant of this is equal to whole square. Okay, and you see that determinant of A is therefore plus or minus 1. Once again, to talk about the map F from O it is the orthogonal group to plus or minus. Sorry. And this is a continuous map. F is continuous. Continuous. F is non-constant. So you got plenty of examples for non-constancies. We take the next example. Let us take the special orthogonal. The set of all A belong the orthogonal are such that determinant of A 1, determinant of A 1. Now you see a typical element of is given by You can see easily check that the determinant of x is equal to 1. It's an orthogonal group. So you see that take this dot this 0 and norm of each of the rows is equal to 1. So define map phi of positive, and therefore phi is a map from S1 to and you see that phi is continuous. What more you have? S1 is connected. So prove this. And therefore, it's connected. Next example. Let f comma g be a continuous map from connected set interval 0 1 to both continuous. Continuous 0 1 and G is G1 equal to 1. Okay. Now we claim that Gx equal to f of x for some x let us examine what is this geometry. What is the geometry? Now G is a continuous function from 0, 1 to 0, 1, defined by something like this. G is some continuous function whose graph may be like this, and there may be many more oscillations possible. So this is G. And F is a continuous function from 0, 1 to 0, 1. So this is something like this. This is F. This is the graph of F. This is the graph of G. What it says is that there is exactly, or not exactly, there is at least some x where fx is equal to gx. Now there may be many more points, because in fact if your f may be something like this, then you see that there are other points also which qualify for this problem. Okay? But what it says is that there is at least one point x with the property that fx is equal to gx. Now here what you make use of is the intermediate value theorem, which is just been established as a consequence of the connectedness property that we have done in our last lecture. If f is a continuous real valued function on the interval ab, and if fa is less than f, then there exists a c, a real number such that fa less than c less than fb, then there exists an x belonging to ab, open interval ab, such that fx is equal to c. That is the intermediate value theorem, which we have already earlier. So let us use that. So define G minus. Then you see that H0 equal to minus 0, because G0 equal to 0, and H1 equal to G F1, and this is equal to 1 minus because we are using G1 equal to. Therefore, you see that H0 is negative, and H1 is greater than or equal to 0. Okay. So this we have got about the h. So h is a function which takes possibly a non-negative value at 0 and a non-negative and a positive a non-positive value at 0 and a non-negative value at 1, and h is continuous. Therefore, by the intermediate value theorem, there exists some x belonging to such that equal to 0. That means if it takes a negative value, if it takes a negative value here and a positive value here, then and it is continuous, then it has to cross this at least once, if not more than once, many times. It depends on how oscillatory your function is. So these are solutions of it. Okay. So again, you are using connectedness in the background. Because we have proved the intermediate value theorem using connectedness. Another example. The annulus x belonging to R2, 1 is connected. So let us define, see, this is the one. This is R2. You have, this is norm x equal to 1. This region that we are talking about. So this is the radius 1 is 0. So this is your A. Now let us take two sets or let me use the notation as now let the interval 1 2 and b equal to the interval now consider A cross B. So you have A cross B is one, 2 and 0 to 2 pi. Is this portion, these two lines are not included, but you have this strip. This is the strip that you have. So this is now A cross B is connected. Now, how to get this annular region from this? Observe that suppose you define f from a cross b to r2 by f of r2. R running from 1 to 2. That means you are taking this. This is r equal to 1, r equal. Okay. And in between. So you get this one and then swing it around using this part of the map. It is b is from 0 to y. Then you define this by r cos t r sine. Then f is from a cross b to omega is continuous. In fact, omega is equal to f of a cross b. So f of a cross b and f is continuous. Therefore, since a cross b is connected, implies omega is connected. Being the image of a connected set under a continuous map. Right. So we give another example. Let me check what is the number. One, three, 4, 5, 6, 7, 8. So this is actually this is 10. Consider a cell which is the unit sphere then plus one dimensional space Rn plus 1. Take the unit sphere in Rn plus 1. This is designated. It's the standard rotation. It's a now define. So we claim that we define f from Rn plus 1 to by now you see that this is something like this. We are working in R2, then what you are having is this. This is the point that we are not considering. Okay. So we are taking R2 slash 0, and then you are mapping every point along the radial direction to this, its intersection with the. So all these points are mapped. Okay. That's the map. What I mean to say is this. This is S1. Now you have expunged this point. That means there is a puncture for the there. Now what you do is, so you take R2, this is connected. Now you are taking the map as this. As all these points are mapped to this. That is every point on this radial line. So this is actually R theta. Is mapped to the point 1, 1 theta. Okay, so this is the map that you are. Okay. Or if you put it the other way around, then it is this. This is the map. Okay. Both these are the same. Two different. So what you have is this. So f is a map, f of x. And of course x not equal to 0. Therefore, on the connected set, to S1. Sorry, Sn. Therefore, implies now one thing in this context is that we have to see is To take the interval, you have say want you can use this notation. It's not correct. But Sn here, of course, n is greater than 1. Okay, so I think that's a nice place to stop. Thank you very much.